Hi, everyone. This is Heidi Dierssen from the University of Connecticut, and I'm speaking to you virtually from beautiful Rhode Island, where the Mashantucket Pequot and the tribal lands of the Mohegans are. Today, I'm delighted to talk about how some of the optical technology we have in Earth's ocean can be applied to exploring other oceans, as you've heard about in this session. Uh, so let's take us on some kind of an analog. I had the pleasure of doing some research up in Svalbard, teaching a couple classes. And so we're going to take a little visit up to Svalbard, to the coral reefs of Svalbard. So here I am in my location on the border with Connecticut. And I'm going to fly all the way to Svalbard, some of the northernmost everything, bars, churches. And in this environment, you can find a lot of diverse life that actually can serve as analogs to other worlds. For example, this is some beautiful imagery from my colleagues at the Norwegian Technical University, Dierssen and colleagues. And you can see so what I wanted to show you there is that it's not colorless, right? So you see that seafloor, you see the Lophelia, those white cold corals, and all of a sudden there's orange ones, same species. We still don't even understand exactly why our own ocean world is so diverse and why we have these beautiful systems on Earth that have colors in the deep where there isn't light of those colors. And so we have a lot of technology we've built up. And today I get to overview. And if I miss one of your papers or technology, just shoot me an email. I'd love to include all of the research that's been doing that you've been doing. I'm just going to briefly talk about sort of four types of optical properties. You might also know about acoustics, and acoustics are great, except they find larger particles. And optics, like on the scale of centimeters. So the unique thing about some of the optical techniques, especially looking at optical properties, they can get down to microns. So if we go to these giant ocean worlds, we may not have large organisms, but we may have the smaller micron sized. So that lends itself towards optical technology. So you all might have known the Argo float program. And I just want to say this is a really good analog for the types of autonomous sensors that we can get a lot of data, and they're low payloads, meaning they don't need a lot of energy. And they can really give a sense on life in the ocean. There's, for example, the oxygen, nitrate, and pH sensors. And then the optical world, we have fluorescence. In this case, we just use chlorophyll A, but you can have fluorescence sensors for CDOM, for other pigments like phycoerythrin. And so we can make a whole array of different types of fluorescence sensors. Particulate backscattering, which is a very good a way to look at particles and how they move in the ocean worlds and where they aggregate and so forth. And then spectral light attenuation. So even in the dark oceans, we can have some light. And as we look at how light spectrally gets changes with depth, we can actually infer things like pigments that are related to light, life, and other properties. So these are some of the sensors on the new and hopefully continuing biochemical Argo profiling floats. There's a recent annual review led by Hervé Claustra, which shows the backscattering of particulates. For example, this is one of our ways to really assess backscattering vertically in the ocean, and where particles can be high and low in just one ocean basin and across the global world ocean. So the future, we're getting better and better with technology at putting these things in ice zones. So that would be relevant to exploring under ice phenomenon on other ocean worlds. There's deep Argo. And I just want to highlight this paper, which is quite unique. I don't know if you can see here, by Henchins and et al. That looked at detecting mesopelagic organisms using biochemical Argo floats. Kind of a cautionary tale, sticking sensors in a foreign ocean. We don't know what might happen. Well, when we put them in our own ocean, we show that migrating organisms can actually be attracted to emitted light. We know this from a lot of the work at Mbari and others institutions when you do put a lighted robot in the ocean. But yeah, so just word to the wise, you may not be seeing the particles you think you're seeing, but you can actually look at things such as diel vertical migration in new ways as well. So those are some of the optical sensors we've developed that do both spectral light attenuation, backscattering, absorption, and so forth. Um, we also can measure light itself levels at really low levels. This is a new book by my colleagues in Norway, Jürgen Berge, Geir Jonsson, and Jonathan Cohen that were the editors that has a lot of interesting things that ecology is really not dormant, but quite active in the polar night. And so as these processes happen, this is an acoustic sensor, but they have a lot of technology for looking down into the dark ice-covered oceans. And they show that even in the dead of Arctic winter, no light, that you can have diel vertical migration of zooplankton under 1 meter of sea ice. And this is shown over these February graphs down here. So that's kind of very interesting. So organisms still are responding to patterns in the dead of sunlight with no sunlight. And this is kind of a cool image from their book showing bioluminescence actually at the ice. So along the shoreline. So it's kind of interesting, a lot going on. And these analogs, like the polar night, are quite useful for thinking about how we can explore in new ways with new technology, these ocean worlds. And so our sensors are getting better. In my day, most of my optical sensors kind of have a signal to noise problem when the light gets really low. And you can see here, this is the course of winter. Our sensors kind of bottom out here, many of them. So it looks like there's no light at all. And if you highlight this box here, their new Arclight Observatory is showing how you can actually see enhancements with just like the full moon. So organisms are quite in tune, even in the dead of winter, to the light changes from, say, a full moon. And we can get better and better at measuring light during these dark winter times, and down to photon level sensors, also of relevance. So that's sort of ways to measure light itself. And then parallel to that, we've been getting lots of exciting new technology to do plankton observing. So this is a nice summary led by Fabian Lombard et al. And it's really amazing. I'll show you this. We have particles going from very small diameter, that's across the x-axis in micron. So getting to the 0.1 micron size to 1 micron to 10 microns. These are these, very small bacterial cells like cyanobacteria and things like that. And then the optical imaging method on the axis on the Y. And you can see that not any one sensor can do the full array of sizes. So you kind of have to think about what sizes you think would be most likely to be observed in these ocean worlds, or come up with, a sensor array that can cover all these different um, size classes. Uh, Now, as the technology increases, we get better at looking at these size ranges and the target for the observations. Here's a whole list of those sensors that I showed you in the previous graph. And for example, some of these are imaging, so you can start to see what is in the water, not just that there's a particle of a certain size. And so, for example, this is from Allison Chase, who's worked up a lot of the imaging flow cytobot data. And you can just see the amazing diversity of particles in our very own ocean and their sizes and shapes and morphologies. Certainly hard to use a spherical model to model the phytoplankton in the world ocean when you see all this beautiful diversity of shapes. And this could also be, these types of things are getting more and more autonomous. They can view in situ in the field and water, requiring a bit more energy than the first set of sensors I showed you. So you have to have, bigger battery systems. But, as technology gets better, these kinds of things are certainly revolutionizing how we look at particles in the ocean. And just a shout out to Allison, who's on my science team. There's a really nice new paper that says that even in our own world ocean, we often use pigments to talk about sizes, thinking that diatoms and dinoflagellates are mostly microplankton, sort of the larger size. And then this new work, she says, that's actually looking at all those different phytoplankton images. You can see that there's a lot of nanoplankton, diatoms and dinoflagellates, and they considerably should be considered in that size class as well. And also, we often say that chlorophyll B is just the smallest picoplankton, but we find chlorophyll B also in organisms that are nano and micro. So we have to rethink about how we look at sizes if we just have pigment information in our own ocean. And then this is a nice review from Nyack and colleagues that talks about holography, which has also come a long way in the last few years, and now they're commercially available as well. And you can actually look at sort of the three-dimensional aspects uh, of particles, in this case, plankton in the ocean. And here's some images from that paper. So the ocean community has come a really long way in actually seeing the organisms, and there's some nice work on how they can line up and they're not random oriented, and how these organisms are moving and changing in the world ocean. All right, so since I'm summarizing, I have to go fast. So those are sort of point or profile measurements, and now I'm going to move to more 2D and sort of lead into some 3D imaging, which is kind of looking at larger scale processes, such as this is from some of the work we did in Norway on remotely operated vehicles, looking at the sea floor. So we can put sensors on these robotic underwater vehicles that can actually image like those cold corals I showed in my first graph, and the colors and the shapes. And here's an example. As most of you know, I work in hyperspectral remote sensing, where we're trying to look at a spectral fingerprint. So almost all the benthic organisms, these are from reefs, different tube sponges, sand, gorgonians. You can see that they all have slightly different spectral characteristics. I like to say it's like a fingerprint. And in most sensing, when you just have a camera, you have an R, G, and a B. And now we're moving into hyperspectral. Here's me as a brunette, where we deployed these sensors into the fjords in Norway to look at these cold corals. And this is just a picture I snapped from the ship, but you can see these bright orange in the midst of white. There's a lot going on in the cold deep of our own oceans. And this is some more work they've been doing with sort of surface-led vehicles and imaging. So it takes a lot of work. These require a light and an imager, so in tandem, to look at seafloor properties. And VEED is also doing some of this work with fluid lensing, and he'll be presenting in the next talk. Just to say that this is sort of the spectral response of our human eye. You can see we have a blue, a green, and a red cone. And, you know, there's some organisms like the famous mantis shrimp that has many more cones in their eye and can see different colors for going into the UV as well, we believe. And you can see that there's many more ways to look at that spectrum of light. We generally call 400 to 700 the visible light that humans can see. And so now we're sort of going into this hyperspectral where instead of just the cameras of the RGBs, we're actually able to look at the full spectrum of light like I talked about. And most of our ocean color sensors up there are multispectral, having a few bands across the visible wavelengths, and then a few in the near infrared and short wave to help us correct for atmospheric properties. And the next gen of sensors, there's Prisma up by the Italians, and PACE is the one that I lead the science and applications team for PACE, which will be a first global hyperspectral mission to look at the sort of rainbow of colors coming off the world oceans. And we've really said that basically as we've started to look at the oceans, there's different bands and different studies, and you can start to tease out some of the properties related to different groups of phytoplankton that we have in our own ocean that we really can't infer very well from the multispectral. And as we go, we keep adding individual bands and important bands. And really, with the hyperspectral, we're hoping to sort of revolutionize how we look at the oceans. And so this is just a dynamic look at PACE. And so I hope that all of you listening will be excited about, as excited as we are. PACE not only will have this hyperspectral ocean color imager, we'll have 2 polarimeters, which I won't have time to talk about today, but is another important aspect, the directionality of the waves of light and how we can use that to infer better atmospheric conditions and also some ocean properties as well. So this is exciting on the horizon to sort of leap us forward into new synergies on how we look at our own world ocean. I will briefly, and these are some of the ways, this is from a review paper on hyperspectral, but I like it because, you know, we have all these new ways to look at the take data, and I didn't touch on modeling, but there's so many ways that we take all that data I showed you and put them in wonderful models. And these are just some examples of how we take a hyperspectral signal, say from a satellite, and we can do all sorts of data transformations. And then we use the spectra as many different ways. We can use them as descriptors, like the hue, that can do clusters and object-based images. We use the spectra as predictors, and we put them into regressions to understand certain properties. You might have seen our chlorophyll algorithms in the oceans. We also have neural nets now that actually can pick out many more patterns that have been doing better jobs in complex waters, decision trees. And then we also have a long history of using the spectra as references, meaning we try to match that spectra using a model. We often call that a semi-analytical algorithm, but there's also different linear matrix inversion algorithms and optimization algorithms, and all this sort of computational power has been associated with our measurements in the ocean. So now the last topic, so I don't take most of your day, is active remote sensing. So I don't really like to think of passive remote sensing versus active because it's all kind of active, but um, I like to start with this riddle when I teach. So this thing all things devours, birds, beasts, trees, flowers, gnaws iron, bites steel, slays kings, ruins towns, boats high mountain, and beats high mountain down. Most of you may be familiar with the answer to this riddle, and that's really what this technology has been based on, and it's pretty miraculous. It's based on time. So we do send down different colors, different wavelengths of the electromagnetic spectrum, um, but it all hinges on timing. So you might have, seen the old subs when we had sonar. Sound is pretty slow, and they're pinging and measuring the time it takes for that ping. Well, now we have time and clocks that are so much better. We can actually measure going from 300 meters per second now, a million times faster the speed of light. So we're measuring the time that light pulse takes to scatter off different particles. And you can imagine the technology to go from sonar World War II now to LIDAR, actively sending out pings of light down to Earth and measuring the time it takes to get back, either from satellites. There's LIDARs up there right now pinging down green light. I sat um, from space down into our oceans and scattering back. And we also use these from aircrafts and drones. And VEED's going to talk about some next gen. Um, but just think, I just like this is a NASA uh, James O'Donoghue, just the speed of light. So you can just sort of, whoop, if I can see it. Whoop. All right, let me not, let's see. Okay, I'm just going to go on if I can. There we go. Oh, the play button is right near the expansion button here on my computer. So let's get out of that. Oh, I'm going to share again. Apologies, everyone. All right. So just to wrap it up, you guys might have known we've been using LIDARs. This is a nice work by Chris Hostetler and Mike Barenfeld et al. On using LIDARs from space that scatter off pulses back to these LIDARs in space. So the time it takes is really the piece of information you're getting from that presently. And it's related to the colors. So you often get green because you want to penetrate deeply into the ocean. And you can see that this is a nice review paper. And then VEED is going to be talking about his next gen MIDAR, which is multispectral LIDARs, and how taking all that data and putting it into his NemoNet AI kind of systems. So with that, kind of bells and whistles, multispectral imaging, just leave you because it's a virtual world with some deep thoughts. Surf the wave of new technology. I hope you get excited. We're putting up a lot of new satellites. We're building new in situ sensors. The world is opening up. And I hope you're able to catch on and really find something that makes you excited. And there are no passive sensors in life. Um, we may call it passive, but let's try to all be active and engaged. Miniaturize your sensors, not your minds, right? So we're getting smaller and smaller and smaller, and we're thinking bigger and bigger and bigger. And I think that's a pretty exciting time in our science. Observe to see the rainbow around you, listen to hear the call to action, and respond like your life depends on it. So let's all try to be better citizens and contribute more and be more inclusive and get inspired and be inspiration. So with that, I'll leave you today. I hope to see you all in person, and thank you for your time. So Let's pause.